In this module, let us discuss some basic properties of adherent and limit points. So we immediately begin with a proposition. Let A subset of R and X in R be a limit point. Then B X R intersect A set minus X is non-empty for all R in R. What this is saying is, if you take a limit point of the set A, then whatever small open ball around that limit point that you take, there is a point in A that intersects this ball, and that point is not X. That means you can always find a point in A that gets as close to X as you desire, but that point is not X itself. That is captured by saying that for each R, you can find a point that is there in this set. Okay. Proof. Now, we know that we can find a sequence xn. These xn's come from A that converge to X, and xn's are distinct. Okay. Now, X possibly appears in this sequence at most once, right? Because this is a sequence of distinct elements, if X were to appear in the sequence, it can appear at max once. Okay, we can ignore this singular appearance and assume xn is not equal to X for all n. Okay, so what I am essentially doing is I am going to remove that one appearance and construct a subsequence and reindex the subsequence and so on. I don't want to belabor the point. I will just ignore this element X and assume that the sequence xn does not contain the element X at all. It never appears in the sequence. Okay, fix R greater than 0. Because xn converges to X, we can find nr in the natural numbers such that X nr is an element of B XR. This is just one of the equivalent ways of formulating sequences, convergence of sequences, the neighborhood or the open topological formulation that we dealt with. For sufficiently large n, the terms of the sequence must in fact all be in this ball. I will not be able to find just one nr. After a point, all the elements of the sequence must be in BXR. Okay, hence XNR is an element of BXR intersect A set minus X, right? Because this XNR cannot be the element X, simply because we have assumed that the sequence Xn does not contain the point X as any of its terms. Okay, well, not only is this proposition true, the converse of this proposition is also true, which I am going to leave as a nice exercise in sequences. Exercise, show the converse of the above proposition. The converse says that if for each r in R we can find a point in Bxr intersect A minus x, then x must be a limit point of the set A. Okay. Now, in some sense, limit points seem to be points for which terms in the set A get arbitrarily close to A, but not just terms in the set A, terms in the set A excluding this point. Okay. Now, another exercise for you. Formulate a similar proposition. Formulate and prove a similar proposition for adherent points. Okay. Well, let me just give a hint. Only thing that will happen is you don't have to do set minus x. Okay. Now, all this motivates the following definition. Let A be a set and x be an adherent point. If x is not a limit point, then we say x is an isolated point. Okay. So, an isolated point is an adherent point that is not a limit point. Well, how can a point be a isolated point? Well, let's look at an example. Look at again the real line and look at this set. I'm just taking an open set AB. Then I'm taking another point C somewhere far away. Okay. Now we already know that the set of adherent points is going to be the closed set AB union this single point C. And we already know that the set of limit points is going to be this closed set AB. So this point C is going to be an isolated point. Okay. So from the formulation, this previous proposition that we have, that a point is a limit point, then Bxr intersect A minus x should be non-empty, and the converse, which I have left for you as an exercise, combining this, we have the following proposition, which is just follows from understanding the meaning of the definitions and the previous proposition. If x is an isolated point of A, then first of all, x must be in A. You cannot have an isolated point of A that is not an element of A. This is simply not the case for limit points. You could have limit points that are not elements of the set A. Second, for some r greater than 0, Bxr intersect A is just the set with x. right? The converse of the previous proposition said that if a point is going to be a limit point, that means that every intersection bxr intersect a must contain some element apart from x. The converse means that whenever it is the case that you have a point such that every such intersection is non-empty as in contains an element apart from x, then that point must be a limit point. But here bxr intersect a is just the set with x. For some r greater than 0, we must have this. Proof. The proof is very easy. Since x is not a limit point for some r greater than 0, bxr intersect a must contain no point other than possibly x, right? We can't directly say that x is there because I'm not assuming, that's the first part, then possibly x. Okay, since x is not a limit point for some r greater than 0, bxr intersect a must contain no point other than possibly x. Okay, now we can find a sequence. Xn in A such that Xn converges to X. Okay, but by definition of convergence, Xn is in Bxr for large n. The only way this is possible is, Xn equal to X for suitably large n. Okay, this immediately shows both parts of the proposition. Both parts immediately now follow. Okay, so we have got an interesting thing. An adherent point of A is either a limit point or an isolated point, but never both. Okay, so here are some basic properties of adherent and limit points. In the next module, we will see basic properties of open and closed sets. This is a course on real analysis, and you have just watched a module on basic properties of limit and adherent points.